I would like to invite Professor Neeraj Rastogi. Neeraj Rastogi ji is very well-known figure, as you all know. And please mute your voice. Dr. Dunga, please take care of that from your side. Professor Neeraj Rastogi trained at PRL Ahmedabad, Georgia Tech, USA, and University of Toronto, Canada. Dr. Rastogi is an experimental scientist working on aerosol chemistry and characteristics through the offline and online field measurements. His major current research topics involve brown carbon aerosol, oxidative potential, and secondary organic aerosol. So, Professor Neeraj Rastogi, may I invite you, please? And please be strict within your time. If suppose you save 2 or 3 minutes, then we can also interact with the audience. Thank you very much. Dr. Rastogi.
Okay, good morning, everyone. First of all, I would like to thank the organizer for inviting me to give this talk. And I'm really pleased to hear very nice lectures since 2 days. And it is a good opportunity for me to share whatever little bit knowledge I have about this brown carbon thing. So in this talk, we will talk about, first we will talk about what is organic aerosol, then what is brown in that, and then why Indo-Gangetic Plain is important, and then what are the characteristics we have studied. So let us start with that. So before I start, I would like to acknowledge all my supervisors who actually taught me whatever I know a little bit. And then my group members who are the actually person who work in lab and field, and they are the real hard worker. And I made this Satish name bold because I am representing his thesis work. And then of course, I would like to thank my collaborators who gave me all kind of support to do the study over Kanpur and Patiala, Professor Tripathi and Professor Darshan Singh. So with this, let us start. So, okay, so what is organic aerosol? We all know about it, that these are the species with carbon atoms, which is covalently linked to hydrogen, oxygen, nitrogen, sulfur, etc., etc. And then we also know that there is a natural source of these organic aerosol, which can be algae, bacteria, fungus, pollen, virus, plant debris, and all. But these are all coarse particles. So these are natural coarse particles. In addition to that, we have wide variety of anthropogenic emissions as well as natural emissions. So they emit VOCs. VOCs, volatile organic carbon, which oxidize in the atmosphere and then find particles in the atmosphere. They are called secondary organic aerosol. So anthropogenic can give you primary as well as secondary. And so this way, whatever aerosols you are forming, they are most likely will be fine particles and will be a mixture of natural and anthropogenic sources. If you see their estimate, this primary organic aerosol may be as large as the dust or sea salt in the order of thousands of teragram per year. But if you talk about secondary organic aerosol, this budget has large uncertainty from 25 to 200 teragram per year. It is a very wide range and it can be even higher. So people are trying to understand more about secondary organic aerosol. Then how much organic aerosol contribute to fine particles actually? So this is nicely summarized by Jimenez et al. 2009 science paper. And what you see here are different urban downwind or remote sites. And whatever this outline you see, green outline, this is the fraction of organic aerosol. So overall, what they say is that it varies from 25 to 75% to the total non-refractory. I'm using the word here, non-refractory. That means we are not talking about refractory component, which can volatilize at 500, 600 degrees centigrade. And this is over rural or urban regions of the world. I'm not going in these details. These are type of organic aerosol with certain instrument we use. This is scale, and which is based on the elemental composition of oxygen to carbon ratio and all. So I will not go in these details, but just to tell overall that organic aerosol is a very, very significant fraction of fine particles. Now what we also know that we have a carbonaceous aerosol in the atmosphere. We have black carbon, we have organic carbon. We know that black carbon is always primary particle and they are absorber. We also know that organic carbon can be primary or secondary both, as we discussed just 2 slides before. And they were considered as scatterer. But recent studies have shown that a fraction of organic carbon can be absorbing, and this is called as brown carbon. So unlike black carbon, which absorbed throughout the wavelength, this brown carbon absorbed near UV and visible region. And this can be primary or secondary both. Although BC is more absorbing, we know it is after CO2, this is the most absorbing component in the atmosphere. But mass fraction of organic aerosol is very high in comparison to BC. And what it means that BRC absorption could be significant. In fact, recent global models estimate that light absorption by BRC in different regions of the world may be about 27 to 70% of that due to black carbon absorption. Now, this is a slide from this Wu et al., which the review article on brown carbon, and it synthesizes the sources and effect of brown carbon. So what we see here that major sources are biomass burning, forest fire, fossil fuel, agriculture. They all produce primary brown carbon. And then you have AVOC, means anthropogenic VOC, B means biogenic VOC. This is going in the atmosphere through various multi-phase heterogeneous reaction from brown carbon. And then there is a hygroscopic growth. Ultimately, they get deposited on the surface. It can get deposited over glaciers also. Yesterday, we have very wonderful talks. We heard about that. So if it is depositing on glaciers also, so overall what people have shown. Yeah. So, okay, before going that, let me just one more thing, that the compound which absorb at less than 400 nanometer, they are hueless, and usually they are primary aerosol, primary brown carbon. Wherever the species which are absorbing at more than 400 nanometer, they are nitroaromatics kind of compound, and they absorb at higher than 400 nanometer. Why is it so? That we will discuss sometime when I will be giving some bigger lecture. Right now time is limited. So what is the effect? That BC and BRC immersed in cloud droplets or glaciers absorb light and facilitate evaporation, dispersion or melting of clouds or glaciers. Further, on average, BRC contribute about 35% of the direct reinforcing warming by global aerosol, carbon-based aerosol. And then why IGP is important? Means we are listening this since yesterday or day before yesterday. So the IGP comes under tropical or subtropical region with a large amount of water vapor, higher UV radiation flux, higher temperature than that over temperate regions. So what it means that we have a favorable condition for multi-phase chemistry and secondary aerosol formation. Deep convection over tropics efficiently lifts substances emitted at the surface into the upper troposphere and increases their lifetime and transport. Obviously, it depends upon meteorological condition. Further, advective transport from the IGP to the surrounding ocean affect marine atmospheric boundary layer and surface ocean biochemistry. Again, it depends upon meteorological condition. Deposition of IGP emissions to the Himalayan glaciers can have adverse effect. Yesterday, we have wonderful talks from Ritesh and Rakesh and Shubha and all, and they were telling about the effect of different aerosol on snow. So overall, depending upon meteorology, regional emissions can have global effects. So with this, let me come to the work which I am going to show. So I will be presenting work from Patiala and Kanpur. And what we do, we take this high volume sampler to the site during certain time period that we decide when we have to take. And after, this is blank filter and this is filter after collection. And after this, we analyze variety of chemical species listed here. In addition, now we also started doing online measurement. So this is what we have done over Kanpur. So we are measuring with aethalometer, with aerosol mass spectrometer, with this particle into liquid sampler, liquid waveguide capillary cell, TOC analyzer. This is PILS LWCC TOC. This is not a commercial system. We assemble it and we run it, and that is why in India we are the only one, and in the world also there are very limited group who actually make this kind of measurement. So we will see some of the results from this instrument also. So overall, we are talking about this carbon-based aerosol. And then just little bit, I should tell that why we measure VRC in solutions that can be water or methanol. Why methanol? Because there are studies who have shown that methanol can dissolve about 80% of the total organics. So that means if you are doing methanol soluble organic carbon, that means in a way you are doing total organic carbon. What it does, it isolates BRC from any other insoluble light absorber like BC or dust. Very high sensitivity measurement through LWCC, which is liquid wave-like capillary cell, which is a 2 meter long capillary cell. It provides better insights in BRC sources, chemistry, evolution, and all. But there is a drawback also, that you lose the information on particle size and mixing state, etc. And this is the schematic of PILS LWCC TOC analyzer. So we will not go in detail. So this will give you water extract. You send it to LWCC, measure ground carbon here, and send to TOC analyzer, measure WCC there. For details, you can see for these two papers for filter based and online measurement. Okay. Now, how we measure absorption coefficient? So this is the formula. Kripa was talking about absorption coefficient quite a bit. Let me just add a little bit here. Absorption coefficient at 365 nanometer is used as a general measure of brown carbon. You are not measuring brown carbon directly. You are measuring as a optical property of brown carbon, and mainly you are using 365 nanometer. Why? Because it is far enough from the UV region to avoid interferences from non-organic compounds, for example nitrate, and humic-like substances, that means humus, absorbed at this wavelength. Remember that BRC is a fraction of WCC or OC if you are talking about methanol. What it means, that this ratio of BRC to WCC or BRC to OC can be varying between 0 to 1. That means all organic carbon or all water soluble organic carbon can be brown carbon, or there may not be any brown carbon in that. And then you calculate mass absorption efficiency using these two formula. So if it is water, so you are calculating like this, absorption coefficient by WCC, and if it is methanol, so you are using like this. Here also we will remember that higher the MAE means larger fraction of BRC in WCC or OC, depending upon what solvent you are using. Okay, now let us see this. This is little important slide, so just pay attention here. So this is a typical BRC spectra. So I have just put four different times of the day. This was done over IIT Delhi. And what y-axis tell you this variability in the BRC concentration. This was absorption coefficient. So higher the value means more the concentration of BRC. And what x-axis tell is the variability in BRC composition, chemical composition, presuming certain type of BRC absorbed at certain wavelength. So whatever you are seeing is the net effect of all BRC species. So variability you can see from the x-axis. People have shown that if fresh HO is exposed to ammonia for a longer time, you can make actually brown carbon. For example, SOA change color from white to brown in presence of ammonia. This browning reaction occurs for a wide range of ionic and anthropic aerosol. But so means what we can have, there can be numerous BRC species with different optical properties. Individual BRC species cannot be identified by spectra alone because it is a mixture of all the BRC. People are trying to do that on multiple levels. So, but molecular characterization of BRC needs very expensive analytical facilities and copious amount of work. So, just to circumvent that, we proposed a novel approach where we use simply BRC spectra to draw the information on broader composition and characteristics of BRC. So, this was a paper in 2019. And what we proposed here, see, these are three plots. So this is over Patiala, and we went there during biomass burning. And we were there for about 40 days. We were collecting day and night samples for 12 hours during daytime, 12 hours during night time. So about 10 days we have collected before burning period, then during burning period, about 15 days, and then again means a couple of days after the burning was over. And what you see here, this red and blue is day and night. And this right axis is the ratio of these two, night by day. So here, what is the concept? That primary BRC, for example, humic-like substances absorb at less than 400 nanometer. We have talked about that. And secondary BRC, like nitroaromatics, absorb at more than 400 nanometer. And what you learn from here, that night by day value of B absorbance at a given wavelength. For example, you are talking about say 400. So if you take the ratio of night by day, you can calculate that what is the change in BRC concentration from day to night. So this is on the right. So about 1.3, you can see means night time concentration was about 1.3 times higher. But if you come to burning period, you see there is a big range, and this ratio, this was varying a lot from as a function of wavelength. So variability in the ratio with lambda. Lambda means when you are changing the lambda means you are talking about different species now. So it tells the change in the BRC composition. So what you can infer from here that during biomass burning, you have a wide variety of BRC species which are highly absorbing in this wavelength region, and then you have hump here also, and then less component from which are absorbing in this particular range. And this is after burning period. So overall, what we saw, what we stated there, that biomass burning emission inject both primary and secondary BRC with larger contribution to primary BRC. However, average composition does not show drastic day and night change during normal days like here and here, because you see it was kind of flat, but you see a hump here. You see a hump here. So that means the species which are absorbing here, they were actually increasing, but all other species were more or less similar. But during biomass burning, it was quite different. And this we could draw just based on the absorption spectra of BRC species. If you see this further, so here this is W7 by OC ratio, which is the indicator of that means higher the ratio means you have a larger fraction of water soluble nitrogenous organic in the total water soluble organic carbon. And this was during daytime, this was during night time. You see the R square here, and slope also you can see. So what you can infer from these two plots that higher nighttime W7 to W ratio were associated with the higher absorption coefficient at 450. In contrast to daytime, it suggests nighttime nitrogenous compounds were more absorbing. See, ratio were similar if you see night and daytime, but absorption was very high if you compare here and here. So that means the nitrogenous component during night time, they were more absorbing. And then we also try to calculate the water insoluble and soluble fraction separately. So what we already have is this absorption factor of water extract and methanol extract represent the bulk optical properties of water soluble and methanol soluble BRC respectively. So using this formula, we can calculate water insoluble fraction. And when we plotted again during T1, T2, T3, what we saw, so here means on this side, you see this water by methanol. So that means what is the water soluble fraction? So if it is 0.4, that means out of total BRC, 40% was soluble, but at this wavelength. But if you are coming to higher wavelength, only 20% or even less was soluble. So as a function of wavelength, the solubility of BRC species are changing. So water insoluble fraction at different wavelength were different during T1, T2, and T3, whichever the three different time period. And observation also suggests that BRC absorbing at higher wavelength were predominantly water insoluble. So this right side axis what percentage water insoluble fraction, which is, you see it is going up to 90%. So that means if you are going to a higher wavelength, these BRC species are water insoluble. Relatively more. Actually, both you can see that it is not crossing 0.4. So that means only 40% maximum at that also at this wavelength only is water soluble. Remaining is insoluble. And then we also calculated the relative rate forcing due to BRC with respect to elemental carbon. So if you see these two plots, relative rate forcing of BRC with respect to EC values were calculated at different wavelengths. The other wavelength for this is for water and this is for methanol. And then this is at 365 nanometer only, and daytime and nighttime. And you see always nighttime was higher than during whatever was there was during daytime. And what we inferred here that at this 65 nanometer, average RRF relative forcing of BRC water is estimated to be about 17%, whereas that of BRC methanol is about 62% with respect to EC. It suggests that BRC relative forcing could be largely underestimated by studies. Those use BRC water only as a surrogate of total BRC. So this is the plot from Srinivas et al. 2016, and here we plotted reported MAE value over different sites. and all but during winter. You remember that higher MA means larger fraction of BRC in WSOC. So here you have higher MA, and as you are going this side, it is decreasing. And we know that during winter time we have a wind pattern like this. So what we say that there is a relative increase in non-absorbing WSOC during transport, and that is why MA is decreasing. Or it could be also photo bleaching of BRC during transport. However, it is very difficult to understand the dynamic changes in BRC composition and characteristics using offline techniques alone. So then we use online techniques. So this is a study from over Kanpur. Now just see, it is shown means around 13,000 data points are here. This is absorption coefficient, this is water soluble organic carbon, and the slope is actually MAE. If you recall, this was MAE, so slope means MAE. It was highly variable from 0.003 to 5.26 meters square per gram. And this was colored as a function of hours of the day. So you notice whenever you have this time period, these all values are lower side, and when you are in this time or this time period, these all values are high. And this is the diagonal trend of absorption coefficient and WSOC. And we divided this into three parts. So night plus evening we put together, morning we separated, and middle of the day we separated. And what we noticed that average MAE during evening plus night hours was about 1.34. For morning hours for 0.95, and middle of the day is 0.58. So see, within the whole day from 0.6 to 1.3, there is a large variability in MAE of BRC. This was attributed to the primary sources, as hydrogen to carbon ratio from AMS measurement was also high. This represents the emission of more emission of primary sources. Morning hours, it was attributed to secondary organic aerosol formation as WSOC by CO ratio. CO is the indicator of primary emission, WSOC is the indicator of secondary aerosol formation. So if this ratio is high, that means we have more formation of secondary aerosol. So since this ratio was also high, so we attributed this to SOA formation. And then during middle of the day, we saw the minimum values, which suggests that BRC undergoes through photo bleaching during daytime, or it is volatile and evaporates with increasing temperature during the daytime. So overall, it depends on the type of chromophore present, which is primary or secondary, and meteorological condition. Here, if you see, these are the absorption coefficient, and these are different AMS derived parameters. I will not go into too much detail. Just see here. This is the linear regression analysis of absorption coefficient with total organic aerosol we have measured. See the slope here, and then with PMF derived factors like hydrocarbon like OA, or low volatile oxygenated OA, or biomass burning OA, semi-volatile oxygenated OA, type 1, type 2, and then this semi-volatile oxygenated OA biomass burning. So what we observed, the order of slope was, this was the highest. Slope was 1.58 for this particular source, followed by HOA 0.97, followed by this 0.77, followed by 0.64, and then 0.38. So more the oxidized OA, less the MAE. So what it means that absorption, first thing is absorption capacity of BRC from different sources are different, and this order tells the relative, you can say that relative capacity of BRC from different source factors. We have not plotted this here, and this was the lowest with the poorest correlation, and this is the most oxidized aerosol. Low volatile oxidized aerosol. So what it means that oxidized aerosol or is organic aerosol does not absorb considerably, or you can say that after emission, as the aerosol get oxidized, their absorbing properties decreases. So to summarize, BRC is a significant but highly variable fraction of organic aerosol. The absorption coefficient of this for methanol is often higher than for water, reflecting that dominant presence of water insoluble BRC. We have talked about that, which cannot be ignored. Observation also does suggest that BRC species absorbing at higher wavelengths are predominantly water insoluble. Further, we have seen magnitude of night by day ratio of absorption spectra over a wavelength range reflect the change in the composition of composition and concentration of BRC chromophores, which absorb at different wavelengths. BRC composition is affected by temperature and photobleaching process in the atmosphere. Primary BRC from biomass and fossil fuel burning are more absorbing than fresh secondary BRC, and oxidation or aging process reduces their absorption capacity. Further, BRC reinforcing could be largely underestimated by studies. Those use BRC, water soluble BRC only as a surrogate for total BRC. And with this, I would like to thank you all for listening patiently. And if there are any questions, I will be happy to answer. So these are some of the studies, our studies for the Indo-Gangetic Plain. Thank you.
So thank you, Professor Rastogi. And one quick question, please, if anybody wants. Because in chat, I am looking that so many questions are raised.
Hi, Neeraj. Can I ask one question?
Yeah, sure.
Okay, yes, Neeraj. So interesting talk. I have just one basic question that is it possible to separate the meteorological aspects in terms of mixing layer depth from the chemistry playing a role, particularly during the night time when we see very high value of the concentration of brown carbon?
You are talking in the open atmosphere or your controlled study you are talking about?
I just want to get your insight into this aspect about the mixing layer depth, the boundary layer dynamics on the concentration of the brown carbon.
Okay, so that is certainly there. So if you recall the ratio when I was showing night to daytime ratio, when you have this boundary layer different during nighttime and daytime, and if you see there was a straight line and then there was a variability in that ratio line. So if there is a straight line, that means composition same, but concentration is increased, and the ratio will tell you that how much it increased. It was about 1.3, that means about 30% increase. But during biomass burning, if you have noticed, that ratio was highly variable. So that means your concentration as well as composition both were varying a lot.
Okay, thank you.
And if we are doing with that was unfortunately due to using filter-based, it was filter-based study. If we were doing this online study, then we would have talked more about this. Then can directly correlate with different meteorological parameters.
Thanks, Neeraj.
Okay, Professor Rastogi ji, thank you very much for your nice presentation. In the series now.